Quantum dots are colloidal photoluminescent semiconducting crystals that have unique optical and electrical properties, which are used in applications ranging from LEDs, solar cells, transistors, diode lasers for site-specific medical imaging, and for drug delivery. Quantum dot synthesis is most efficiently done by the method of colloidal solution. This approach involves controlled arrested precipitation from colloidal solutions. New approaches for quantum dot synthesis have been successful where the manufacturing is more rational, utilizing modern engineering techniques and non-volatile intermediaries. Optical properties of quantum dots derive from their surface properties. On the surface of these quantum dots, unsaturated dangling bonds and poor surface passivations with organic ligands can increase the proportion of the trapped state emission or non-radiative recombination, which leads to a low photoluminescence quantum yield. In addition, these factors also lead to a poor stability and the quantum dots. The stability of quantum dots have been improved through encapsulation in SiO2 and Al2O3 and the surface modified by its core shell structure. Light-emitting diodes are semiconductors that emit light through electroluminescence, where energy is released under the influence of an electric field. LEDs have many applications ranging from aviation lighting, automotive lamps, advertising, and general lighting. There are various types of LEDs included inorganic LEDs, organic LED, and quantum dot LED. Quantum dot LEDs have the ability to exhibit pure and saturated colors with a narrow bandwidth. Emission from the quantum dot LEDs can easily be tuned by varying the size or the composition of the quantum dots without changing their processing properties. In quantum dot LEDs, quantum dots are placed where the exciton decays or electrons falls through a hole and releases a photon. This is beneficial because quantum dots are an inorganic material that are less prone to photobleaching, as they show a higher photostability and their electro-optical properties can be modulated by adjusting the size without changing the chemistry of the synthesis. Superiority of quantum dot LEDs over organic LEDs is due to their chemical and optical stability, tunable emission wavelengths, high color saturation, and workability. Although both quantum dot LEDs and organic LEDs contain an organic polymer base, quantum dot LEDs are different than organic LEDs in that the polymer also features a mixture of quantum dot precursor that are activated by thermal treatment.
A 3D particle in a box is similar to a 1D particle in a box. The energy E is a representation of the combined energies of particle in the x, y, and z directions. The wave function is also modified to accommodate the extra dimensional spaces. This modification allows the energy levels of particles or the excited states of an atom to be determined. The free charge carriers of quantum dots experience quantum confinement in all three spatial dimensions, similar to a particle in a 3D box. Quantum dots have electronic properties similar to both semiconductors and discrete molecules with similar shape and size. These similar electronic properties allow the properties like band gap, emission color, and absorption to be adjustable during fabrication of the size distribution of Q dots. Quantum dots with electrons are similar to atoms in that they have discrete energy levels and a small amount of electrons. However, the confinement potential of quantum dots does not need to be spherical symmetry. The quantum dots electrons move inside the host semiconductor crystals. Q dots are compatible with solution processing techniques. This is due to their small size that allows them to be suspended in different types of solvents.
The complexity in the geometry of quantum dots can lead to various problems in their theoretical descriptions. For example, it can be fairly difficult to construct a realistic Hamiltonian for quantum dots. Other methods must be used, such as perturbation theory, variational theory, adiabatic method, finite element method, and others. The Hamiltonian of a fast subsystem includes variables as parameters from the slow subsystem, and the h of f represents the fast subsystem, and the h of s represents the slow subsystem. The reason there are slow and fast systems are because it follows the geometrical form of a conical quantum dot that the particle motion along the radial direction occurs more rapidly than along the z direction, which allows one to use the adiabatic approximation. Quantum dots are currently used in technologies such as televisions, however, in conjunction with LCD and blue backlight LEDs. Usually, a tube of blue LED is placed as a backlight behind the LCD screen, which provides the excitation energy for the red and green quantum dots to wrap around the tube to display images on the LCD screen. This technology has produced bright images and can be seen on some Samsung models today. But television is classified as an LCD instead of an LED because of the screen technology. Furthermore, OLEDs and plasma televisions have better contrast ratio between colors than LCDs, which makes OLEDs the best in television market until quantum dot LEDs are manufactured past prototype. Quantum dot LEDs will have the same superior contrast ratio OLEDs have, but will produce brighter and clearer images due to quantum dot narrow bandwidth and saturated colors. In addition, OLEDs create a white light from yellow and blue using LEDs materials, which can only create colors with red, blue, green, and clear color filters, therefore suffer a loss of efficiency. Quantum dot LEDs, on the other hand, can actually emit the desired colors with the quantum dots. Larger quantum dots emit the bright red light, while the smaller quantum dots emit bright blue light and the other colors in between. Quantum dots LED television won't be available for 3 to 5 years because companies like Samsung and others are keeping their advancements top secret. Quantum dots are currently finding applications on making the best LCD screens. However, their full potential will not be available until full quantum dot LED screens make their debut.